So this is build up your understanding, question 15 from the book Pathfinder from the chapter of electromagnetic induction. So question is, there is a long solenoid of radius r, it has n turns per unit length and it has a current I. So you can these two figures. So there are two cases. First case is for first figure and second figure corresponds to the second case. And in first case, there is a cylinder now, which is inertia-less. It is a paper cylinder, which does not have any inertia. Its radius is less than the radius of solenoid, right? First case. And length L, it is inserted coaxially, so axis is same, at the middle of the solenoid. And in the second case, the same thing happens in second case, just that now the radius of cylinder is more than the radius of solenoid. Now paper carries uniform charge Q over its curved surface. So on this curved surface, uniform charge Q. So this is the question now. If current in the solenoid is suddenly reduced to I by eta, some factor, then we have to find angular velocity omega acquired by the paper cylinder. We have to ignore gravity. Okay, fine. So let us see how do we proceed. What is the concept here? So it's a very conceptual question, very, very important question for JEE advanced. So here I'm going to use this concept, right? Some of you might be knowing this before. That is, if you know this, you can just revise it. Magnetic flux cannot be changed from a superconducting coil, right? So I'll explain you the reason also. Superconductor means resistance is 0. And these are two equations, right? E is equal to minus d phi by dt. This we know, this is Faraday's law. And current is E by R. Here R is the resistance of any coil. Fine. Now see here. I'm writing this equation as E is equal to I times R. So if you understand this equation, then you understand this sentence also. So what I'm claiming here, that since superconductor, the resistance is 0, right? So then that makes E also equal to 0. And I can be anything which is non-zero. Fine. So is this understood? So R is 0. That makes E 0. I might take any non-zero value. So there might be a current in superconducting coil, but there will not be any change in induced EMF. So if there is no change in induced EMF, then there will be, from Faraday's law, there cannot be any change in flux. That is what is written here, right? Very, very useful property of superconductor. So the same thing I've written here, you can just go through this. Okay, so let us move to the solution now. See, understand, how do we apply this thing here in this case, right? So since cylinder is inertia-less, understand this, again, a very logical point and a very, very important point. Cylinder is inertia-less, it does not provide any resistance to rotation, right? Till now, nothing about current and all. If something is inertia-less, then that means there is no resistance for rotation. It can easily rotate, torque equal to I alpha. Okay, fine. Now, since it can rotate freely, understand this, that means charge is there on the surface. So if it can rotate freely, that means charge can also move freely. You're able to understand, right? Charge can also rotate freely. So rotating or movement of charge is current. That means if it can rotate freely, charge also rotates freely. What does that imply? That implies that there is no resistance to the current. That makes it a superconductor. That is why the cylinder can be modeled as a superconductor. So if you understand this much, then after that you can solve by yourself also. So what we are going to do now, since it is a superconductor, the flux initial and flux final should be same. This is the equation. We are going to get the answer from it. Initial flux is what? Initially, this is not rotating. So mu naught Ni pi rp square. This is the initial flux. Magnetic field inside the solenoid and the radius. Rp is the radius and area, right? Phi equal to Ba I'm using. Fine. Now, final flux will be what? Current reduced to 1 by eta. So mu naught Ni, I becomes I by eta into pi rp square. This is the flux due to solenoid, but it will start rotating. Why? So that it has to make up for the remaining flux. Flux cannot be changed. So whatever flux you have reduced, it will acquire its own flux by rotating. So how do I now calculate its own flux? Let us say it starts rotating with omega. Come here now, see. Then what is the magnetic field of solenoid? Mu naught Ni. N is number of turns per unit length, we know. Number of turns per unit length can be written as total number of turns divided by its length. Now, Ni we can think of as the total current in the solenoid. and L is the total length. So this is total current divided by total length. Mu naught di by dx is also the formula of magnetic field inside a solenoid. Fine. Then this is current per unit length. Now, how do we apply this formula for our case? For rotating cylinder, what will be the current? Total charge is Q, and since it rotates up with angular velocity omega, time period will be 2 pi by omega. Q by T formula I have used. Q by T, so that's the current. But we need current per unit length. Current per unit length is Q omega by divided by the length. What is this length? This length is this L. This is current per unit length, right? So magnetic field is this. Mu naught di by dx is the magnetic field created by its own rotation. Fine. This has to make up for the flux, which is gone, which is reduced due to the reduction of current. So that is what why there is a plus sign. That is obvious because of the Faraday's law you can understand, and Lenz's law you can understand. So I've written this: since flux is reducing, its own flux will support it. Lenz's law. It opposes a change. So that's it. Now in this pi rp square you can cancel, and if you solve, you get omega as this. This is the answer of first question. Now for second one, I've just written the equation and left it. For second one, phi I equal to phi f. Now here, initial flux is mu naught ni into pi r square. R is the radius of solenoid because you don't have any electric field in this annular region. Then after that, this is the flux mu naught ni by into pi r square again in that magnet. But when it acquires angular velocity, this is magnetic field, right? This I have already explained into pi rp square. So from here now you can calculate for the second case, right? So it's a very good question of superconductor and highly probable for JEE Advanced, even more probable for Olympiad exams. So if you like this analysis, please hit like button to this video and share this channel with your friends. Thank you very much.